Sí, bueno, okay. Good afternoon, everyone. Welcome to International Material Research Congress 2022. The next plenary conference will be given by Professor Nid Birbilis. Welcome, Professor Nid Birbilis, a Cancun. The Professor Nid Birbilis is interim dean in College of Engineering and Computer Science in Australian National University. His research and broadly in the areas materials designs, metallic materials, materials durability, and corrosion. He was awarded his PhD from Monash University in 2004 and has worked in areas that cover phase corrosion and electrochemistry. He was previously the Woodside Innovation Chair at Monash, where he was head of the Department of Material Science and Engineering. He is the fellow of the National Association of Corrosion Engineering, NACE, USA, fellow in the Electrochemical Society, ESCS, and fellow in the International Society in Electrochemistry. Come on, please, Professor Nid.
Thank you very much, Facundo. All right, it sounds like my microphone is on, so I'm going to get started. It's a real pleasure to be here. This is my first time in Cancun, and it's been absolutely amazing. Today I'm going to be talking about one of my favorite topics, which is the corrosion and passivation of engineering alloys. So before I begin, I just want to say a very special thanks to the conference hosts, the Mexican Materials Society, MRS, and the International Union for Materials Research, and of course the organizers for IMRC and ICAM. The picture that you see there actually is a traditional picture from Australia, which is where I'm from, if you hadn't picked up the accent. And what we tend to do in Australia is, before we start a presentation, we usually acknowledge the traditional custodians of our land. So I'm not in Australia right now, but I would like to pay my respect to the people of this area and of course the Mayan people as well. So this is potentially a very, very huge topic. And so what have I done? In order to try and break it down a little bit, I'm really just going to focus on engineering alloys, which are largely what we know as structural materials. It can be other things, of course, but I wanted to just break down what could potentially be a very, very big topic. When I'm talking about structural materials, I think of things like, the materials that we use for bridges, for aircraft, for creating our fuel, smartphones, and even building our cities. So materials, are the cause for things that attract investment. They make our modern way of life possible, and this is, of course, no news to people at this particular conference, right? Particularly metallic materials, which are completely inorganic, and that's something that's going to be a common thread throughout this presentation. So not just existing materials, but I like this example here. This is a bit futuristic, but this is a collaboration between Audi and Airbus called the Pop-Up. Whether it will happen or not, I don't know. But I like this example because it reminds me to let you know that future materials needs are always continuously emerging. So when you look at something like this scenario, we're going to need new materials for this sort of vehicle, right? So currently when we think of propulsion systems, very expensive, not commodity materials, very specialized, and of course using materials in environments that we haven't previously conceived. So a really good example is even our laptops, right, and mobile phones. Materials weren't generally designed to be in contact with human hands for very, very long. And the way in which those materials have evolved, including the aluminium alloys used, the conversion coatings on magnesium alloys, the way things are anodized, have all evolved in response to sort of future needs. And there's a lot of future needs. If you think about things like aviation flying higher, faster, if you think about space, there's a whole range of different things. So I really do like that example. But when we're thinking about old or new materials, I'm going to take a little bit of poetic license for a moment, as a corrosion person can. It will make sense in 30 seconds. But basically everything that we make as far as structural materials go, it doesn't just come from a factory. It comes obviously from planet Earth. And so if you look at what our planet looks like, we get down to ores and we get down to minerals, and we use a heck of a lot of energy, a huge amount of energy to go from the ore to the periodic table. Now, I can't cover everything, but specifically when we're talking about metals, I think it's no news to everyone that metals specifically don't really exist in the natural state and the sort of volume you would need for engineering materials. So we have to process them, put in a lot of energy, and that's really the basis for the things that we enjoy today. So we kind of act like God in a way. So the way in which many of us got here, certainly the way I got here, is we take this route of where you have a planet, you have engineers and scientists and chemists and physicists like us that create materials that we can use. What's important to realize is that the materials that we use are what we call anthropogenic. So they chiefly are of environmental pollution that are because of the human activity. So what happens, right, when we go from here to here? There's a lot of money, a lot of energy, and I'll show my first equation, but free energy wants to drive this backwards, right? And we talk about corrosion quite a lot. There was a whole 2 days worth of wonderful talks actually at this conference on corrosion, and it was mentioned several times that corrosion costs most developed nations about 3% of the GDP. So the problem is not so much corrosion. That's going to happen. The problem is, what are we actually making, and what are we doing here in this transition that makes this want to happen so easily? And of course, fortunately, it doesn't happen super easily because of this phenomenon known as passivation, but it still does happen easily, and that's something that I'll try and cover. But in terms of social responsibility, the question is always there: how can we be more sustainable to avoid this? And of course, how can we have materials that are more durable to allow this? And so I'm going to talk about passivity a little bit, or for rationalizing corrosion. It's going to be a bit of a crash course in case some of you haven't done anything with corrosion before. But probably about 70 or so years ago, things like pore bay diagrams started to become important. Now, these are thermodynamic diagrams that really talk about the tendency for metals, and I call them inorganic, not because they don't have carbon in them, but they're human-made materials. How do they sort of behave? And so pore bay diagrams are really just a manifestation of the Nernst equation. You just put in the calculations, and chemists, electrochemists know that the Nernst equation works. And you can see across a range of pH and potentials, you get these different fields. Now, the one I'm showing here is for magnesium, because in real time, you can see corrosion. So this is just in water, right? Neutral pH, nothing special. You can see it dissolving, and hydrogen is evolving as the cathodic reaction, and you get corrosion. So that's a manifestation there. I'm not going to show you a video of passivation. This is my one joke for the evening, because you'd see nothing, right? If you had a video of passivation, it's just not doing anything. But what we mean by passivation, and this is pretty much a 100-year-old sort of image of what people consider passivation to be, is you have your metal or your alloy, you have a passive film that forms on top in response to reaction with the environment. Now, the environment is usually atmospheric conditions, could be at high temperatures, it could be, whatever environment your material is exposed to. You have a film that then creates a barrier between the electrolyte and the underlying substrate. I guess it's probably known, but I should probably say it, but the way passive films grow is they don't sort of grow like flowers out of the ground. They grow by the interface moving into the metal or the material or the alloy, because that's the source of ions and atoms, right? So this is what we think of as a simplistic view. This particular phenomenon can be drawn in many, many different ways. This is a schematic of a potential drop across this particular interface. And the reason why I'm talking about this is there's been a number of theories over the last century regarding passivity. Some of the well-known ones are the sort of Cabrera-Mott model. You've got the Vervet model and so forth. And these try and relate passive films with either applied potentials and currents and growth laws that give us some sort of sense of what's happening. But what we do know is that this is overly simplistic, and it took a little while to get there, right? This is just one picture, and it's from 2020. But it really wasn't until maybe the last 2 decades that scientists or electrochemists started realizing that passive films are not these well-behaved blobs that obey these wonderful models like the Vervet model and so forth. They're actually usually multi-layered, where you've got a layer sort of closer to the substrate, an outer layer and an inner layer perhaps, and you get different concentration gradients through these passive films, even though they're really thin. So after being in Cancun a few days, I'm a little bit relaxed. So I forgot to say that this is just one example of 316 stainless steel, which is an iron, nickel, chromium, molybdenum alloy, which we all know. So this is usually what your cutlery is made out of. And you can see that you have a nickel-rich inner layer, and then chromium-rich, and then a molybdenum and iron-rich outer layer. So where I'm going with this is there's some complexities, and probably the best rationalization, and I don't want to be biased, because at this point when this was developed, it wasn't the best rationalization, but we'll get to that in a little bit. But a more complicated rationalization of passivity was given by this point defect model, which was conceived by a guy called Digby MacDonald, who was at Ohio State and then moved to Penn State. And he's been working on this since around about 1980. This just came from one of his reviews. So it's now about 40 years old or so. And he put together a series of conservative equations with two that are not conservative equations, 3 and 7. You don't need to know these equations, but this one relates to the rate of change of the metal barrier layer, sort of the metal oxide interface, and then this one is a sort of oxide liquid dissolution. So these are the non-conservative ones. And this was a hypothetical scenario, and the techniques to sort of prove is this the case haven't really existed since recently. So anyway, now you're all experts in passivity with that little bit of background. So now that you all understand passivity, what I wanted to do was spend the rest of the talk talking about contemporary aspects of corrosion and passivity, but using an example of high entropy alloys. I could have used many examples. I worked on many systems in my career, but I thought this one would be an interesting one because maybe some of you don't know about these alloys. They're quite new and they're very interesting, especially from a corrosion perspective. So high entropy alloys are alloys that were conceived simultaneously in Taiwan and in the US around about 20 to 25 years ago. And if you haven't heard of them, you'll find this interesting, perhaps for the first time. If you mix in relatively equal proportions, usually 5 metallic elements, you can create alloys which are notionally single phase, right? So everything you know about metallurgy is when you add something to something else, you get immiscibility and you get phase formation and so forth. So if you take an alloy and you have 20% of any metals you can think of, let's say zinc, tin, gallium, iron, and nickel. Conceivably, this theory of high entropy alloys says it will be single phase. And interestingly, those that conceived them found many examples, right, of this happening, which is kind of remarkable from a metallurgical point of view that this is happening, I guess, in our era or our career. So this is what an atomistic model looks like of this alloy, which is cobalt, chromium, iron, manganese, nickel. So a lot of transition metals there. All right, so high entropy alloys, what are they? They're nominally single phase materials with 5 or more elements, usually in equiatomic proportions. They have a high entropy of mixing, and you can design them using empirical rules. So what that means is, calculate the entropy of mixing, and if it's above a certain number, greater than a certain magnitude, then this effect should happen. And the way in which you estimate that it would happen is if your valence electron concentration is above a certain value as well. So there's like 12 rules that if you follow, you'll get this. But what actually has been happening since high entropy alloys were sort of conceived is several research groups have tried these, and they've got a different notation now called compositionally complex alloys or complex concentrated alloys, which when they're not single phase, this is a classification for alloys that can be multi-phase. Sometimes they have less than 5 elements. They might have 3 or 4, and the entropy doesn't matter. So this is a broader family of things. And then since then, in the last couple of years, you'll find people calling these alloys multi-principal element alloys as well. So what that means is forget all the rules, provided that you have an alloy that just has more than one principal element, it classifies as a multi-principal element alloy. So before, when I was talking about stainless steel, that's got about 70% iron. So that's a single principal element. There's one element that has the majority. Pretty much most of what we use as engineering materials, like pretty much everything on an aircraft, the aluminium alloys, the titanium, the nickel alloys, have a single principal element. So this is a bit of notation for you. Interestingly, like I said, conceived about 20 years ago, literature in the area started sort of increasing, not by a lot, but gradually increasing sort of non-linearly after about 2013, and this is now nearly a couple years old, so it's continued to go up. We got really interested in these alloys because I've been obviously working in metals from back here, and we would make a lot of metals, and when I heard as a metallurgist of these systems, I thought, we've got to try this out. And part of the reason why it was sort of exciting too, in a review by Peter Liao's group some years ago, so nearly 10 years ago now, they did a summary of the high entropy alloys that people had tested, and they found extremely high hardness and extremely high sort of yield strengths, even though the alloys were largely of a high density because of the way in which they were made and produced and the combination of elements that people used. You had very, very high strength. So some of the best mechanical properties that had ever been recorded in these alloy systems have emerged only about in the last decade, right? So really, really interesting. So I became interested in them about 11 years ago or so because our group produces a lot of alloys. We have casting, we have selective laser melting, direct laser deposition. You can see here laser powder bed fusion, 3D printing. We have spark plasma sintering, arc melting. And the reason why they were interesting for us is, if you recall this slide before, you've got all these wonderful properties. We thought, wouldn't it be great if you could make them in net shape and conceive these properties? When you make something in its final shape, then it's ready to use. So we did that. But contrary to high entropy alloys, we were successful at making these things that I called before as compositionally complex alloys most of the time. And that's because we had multiple second phases, not often just one second phase. We had 2, 3, 4, 5, 6, lots of second phases. It wasn't so much a failure, though. It was really interesting, and we got to learn how to make these very complex things. But like any corrosion person would do, right, we thought, big deal, we've made these things. They're not single phase. They're not necessarily high entropy alloys, but they have a high entropy of mixing, and they're multi-phase. We're going to actually just test them anyway. Why not? Because it's fun. And at the time, the reason why I put this here, this is a picture of a guy called Professor B.S. Murdy, that at the time was at the Indian Institute of Technology in Madras. He's now moved to Hyderabad. But the reason why I put him there, he was visiting Australia at the time, and he was also interested in high entropy alloys. So over a period of months, back in India, he made a bunch of high entropy alloys, we made a bunch of high entropy alloys, and we ended up filling a box of like dozens of different compositions. And we gave them to a graduate student, a guy called Yao Chu, to test their corrosion properties. So what did we see? Not what we expected, right? And this is as recent now, starting off this work as 2017. Not what we expected. So I'm going to show you here a polarization curve. And before I talk about them a bit more, I will apologize because I know many of you haven't seen them before. But like I said before, when you're talking about systems with low corrosion rates or passivity, you can't look at the dissolution or measure weight loss. You need to use electrochemical methods. So basically what we see here, you can consider this analogous to a tensile test. When you apply a certain potential, equivalent to sort of applying a stress, you measure a certain current, and you could think of that as sort of strain. So by increasing the potential, normally what you'd see if you had a lot of corrosion is you'd see these curves sort of move off to the right and current would increase. But when you don't see that, this sort of flat bit where you have an insensitivity of corrosion to changes in potential is called the passive range or the passive window. And what we were really surprised with was that we just picked one of the many alloys that we tested. So this is a high entropy alloy. I won't bother talking about the notations, but what this means is it has less titanium than it has each of these elements, so it's not equiatomic proportions. And the reason why you'd sometimes deviate from equiatomic proportions is when you're calculating a composition before you make it, you want to make sure you have a high entropy of mixing, right? Because that's part of the process. All right, so this was really, really interesting. If there's corrosion people out there, you'll probably say, holy moly. Typically, when you see a lot of passivity in our world, you normally have very uniform microstructures. Microstructural heterogeneity is usually a killer for corrosion because you normally get microgalvanic cells forming, you get localization of anodic reactions, cathodic reactions, really bad things. So from my point of view, this particular alloy, these are some SEM images. You can see here, it's truly multi-phase. There's at least 2 other phases other than the matrix. And to see this for the first time, I thought, oh my God, this can't be real. Try it again, do it again, do it again, do it again. Obviously did it again, and this is in seawater. So then we did it again for other alloys, including those that had a very heterogeneous microstructure, and we still got windows of passivity. And then we got it again and again for very strange alloys. Like, look at this one. This is titanium, aluminium, copper, iron, nickel. So I guess other than the titanium, this is kind of a bit of a garbage alloy, right? But still a big passive window. Still a big passive window here for this one. And then the reason why I show this one with the video, I don't have time for everything, you still saw passivity in this particular alloy, albeit with some variability. And that variability, I won't talk about that today, but that was a result of the process that we used to make it. So that was done by direct laser deposition or directed energy deposition. So this was made by spark plasma sintering. This is made by arc melting. So I'm just showing a different variety of how you might actually make these things. So it turns out that we were completely flawed and that these high entropy alloys, by and large, were really, really corrosion resistant. So what did we do then? before we went into all the details and the fundamentals, we thought this is really exciting. What can we try that's really cool now that we've discovered something that we think is perhaps universal across this alloy system? So if you remember earlier, I showed you a plot that had high entropy alloys being very high strength, good mechanical properties, but also very high density. So their specific properties weren't that good. So I thought, wouldn't it be great if we could make really light ones if they're going to be really corrosion resistant? That's much better than, say, using stainless steels or using other materials that are usually quite heavy if corrosion resistance is the key. So what we did is we look at the periodic table. If you look at iron as the baseline, it's got a density of nearly 8 grams per cubic centimeter. And you cross out things that are sort of dangerous or explosive in red, things that are sort of toxic or gases you can't use. And all that's left is these sort of elements with this sort of purple thing around it. And so what we did is we started calculating high entropies of mixing for combinations of those elements. You can see here just the hypothetical alloys, their density, wanting it to be less than iron. You can see here the entropy and the enthalpy of mixing, and you can see the valence electron concentration. So some of these parameters that you calculate, you can see they all have a high entropy. And in looking a little bit closer, we thought of which ones of the low density are probably the easiest to make. And it turns out it was this sort of 4-component one, aluminium, titanium, vanadium, chromium, which has a density of less than 5. Here's the student Yao that did it. And this was a collaborative project actually with Hamish Fraser at Ohio State that helped out with some of the characterization there. So we made the alloy, and it turned out it was single phase. And this XRD pattern was collected on the synchrotron, very high resolution, showing that it was single phase, and it was a BCC phase, but it's a very special type of BCC phase known as a B2 phase, which is an ordered BCC phase. Now I thought, since there's a bit of time, I also wanted to just show a bit of characterization too, just so that people don't think corrosion people don't characterize stuff. So the alloy, when you actually make it and test it, the density was a little bit over 5 grams per cubic centimeter. It was single phase ordered BCC. It's corrosion resistant, as you'll see in a moment, but very uniform distribution of all the elements in each grain. That's an EDS map on SEM. Same in TEM, so this is a scanning TEM image, and even same with 3-dimensional atom probe. And what's interesting with atom probe is you can calculate the compositions from the atom probe data directly, and you can see the equiatomic proportions of this particular alloy was successful. Now, using atom probe data, in case you folks want a bit more insight into what an ordered BCC is, what you can do is you can work out things like nearest neighbor distances for the different elements, and you can do short-range order analysis where you can look at the pairs of the different atoms, and when you have a positive short-range order number, that means that you have sort of dissociation of that pair, and when it's negative, you have association. And so I'll cut a long story short, but what the ordering in the BCC structure is that in the center of the cube, aluminium prefers to be there, and in the corners, from this data, titanium prefers to be there. So there's some periodic arrangement to the way that the elements are in this alloy, even though it's a solid solution. All right, but I'll just put this up by itself because I think it merits its own slide. As far as I know, there's a lot of corrosion-resistant alloys out there. But we got really excited when we did the corrosion rate testing of this, where we saw across a range of pH a very huge window of passivity for this particular alloy, with also what's a very favorable hysteresis. So it repassivates quickly after it starts to dissolve. So pretty much, I'm going out on a limb here, taking some poetic justice, but it turns out that this is one of the most corrosion-resistant alloys that was made by a series of consequences that came from sort of accidental discoveries in the last sort of 5 to 10 years, which is really, really interesting. And you probably wouldn't think that from this composition that you would get this. So then the question is, how do we rationalize this, right? This is what I'm going to talk about now. And what is the surface film? Because you are all experts in passivity now. What's the surface film? All right, so before I jump into what the surface film is, I wanted to introduce a relatively new technique in the area of electrochemistry, which is atomic emission spectroelectrochemistry. This was invented probably about 15 years ago in France, in Paris, by a professor called Kevin Ogle that used it to test steels. He actually used to work for ArcelorMittal and invented this in industry, but now he works at one of the institutes at Chimie Paris Tech. And basically what you have is you have a potentiostat and you have a normal electrochemical cell, a 3-electrode cell, but your electrolyte flows through the cell past your working electrode, and sometime after passing your working electrode, you adjust, for a little bit of a time delay. It's fed into either an optical emission spectrometer, an ICP instrument, or an atomic emission or a mass spectrometer as well. So depending on what you're looking at or what machine you have, it can be optical or atomic emission or mass spectrometry. You can actually measure the dissolution very, very carefully by measuring all the ions that are coming off the surface. So this is genius, this method, because you get ground truth corrosion rate data during polarization, but it's the only technique actually that can give you the corrosion rate at open circuit, because you're just measuring the dissolution with extreme accuracy. All right, so what does this show? As you're looking at the polarization curve, what you can see is a solid line, which is what you'd see from your potentiostat, which is one of these lines. But what you're actually seeing here is the element resolved dissolution current from each element. And you can see they're in different positions. So what you get is you get incongruent dissolution. Interestingly, you don't get very much dissolution of titanium. You get transpassive dissolution of vanadium and chromium. You can see that different things are dissolving at different rates, which is, of course, one thing that we now know is a characteristic of most alloys. You get incongruent, non-stoichiometric dissolution. That leads to very high resolution sort of XPS here on the passive film. And what I'm trying to show you here is a lot of information. I'm really, really sorry. So you could think of what's the passive film on this alloy, either at open circuit or at some positively biased potentials in the passive film. Now, we could pick any of these and it's the same story. So I'll just pick the one at open circuit, which is the native passive film. What we found for this particular alloy was something that we hadn't seen before in other alloys, whether it's nickel alloys or stainless steel. But it turns out the passive film has a pretty big proportion of unoxidized metal. So that's metal in the zero oxidation state. So unoxidized metal means you have metal atoms sitting happily in the passive film. And of course, what you see here is you see sort of a complex cocktail of other elements in the passive film in non-stoichiometric ratios. So the passive film is even more complex than we actually would have thought, and actually includes a lot of unoxidized metal, which is really, really interesting. And these are characteristics actually quite universally of high entropy alloys, and are a bit of a clue as to why they're so passive. When you compare the electrochemical characteristics of the passive film evolution on this particular alloy, these are from two separate experiments. There should be a break in between. But when you sweep the potential, the thickness of the barrier layer actually increases linearly with potential. Once you pass different regimes, when you start to get some transpassive dissolution, the passive film thickness or the barrier layer thickness changes the kinetics in which it's made. But when you hold at a certain potential, the rate of change of the passive film, so the barrier layer thickness, is exponential. And of course, you get these different regimes at different potentials. So this is actually consistent, completely consistent with the point defect model, which was sort of conceived some 40 years prior. And we even dragged out Digby MacDonald to help with this particular work, which was just fabulous. So it turns out that if you were to now draw what's going on in this particular alloy at the passive film and sort of superimpose what the point defect model equations are like, what you'd see is a really interesting thing, and I'm not going to bore you with all the equations, but you see certain things that that you've got these sort of yellow dots here that are the sort of unoxidized metals. Why that's important is that they actually can accommodate strain in the passive film, and we think that's really, really important for increasing passive film stability. And I'm not going to go into a lot of details about all various bits of point defects and sort of cation interstitials and anion interstitials and oxygen vacancies and so forth, because I think it's probably a bit heavy for a plenary. But you get a sense that there's something physical from this remarkable sort of performance. All right, so I'm going to cut a really long story short, and this is somewhere where I've sort of been directing a lot of my focus recently, and how do you use this sort of now newish knowledge about what constitutes passivity and start to think about really corrosion-resistant materials. And it turns out, actually, if you ask yourself the honest question, maybe we should have known about this a lot earlier as sort of engineers and scientists, because there are rocks out there that have been around for billions of years, right? And if you look at those rocks and you do XPS and then you move to the sort of geological community, you can see that these very stable rocks that they have and minerals actually have oxide compositions that are very, very, very similar in this sort of context. Quite a lot of unoxidized metal and non-stoichiometric oxide films that promote stability. So it turns out that we probably should have known that rocks were the most stable thing anyway, but that's a little bit of a clue there. But look, while I'm sort of going on these high entropy alloys, what I wanted to do was also think about how do we advance this knowledge and do actually even more interesting things with this sort of knowledge that we have. So in a project funded by the Office of Naval Research in collaboration with NC State and Professor Rajiv Gupta, we wanted to make low density alloys but that were quite unique. Very low density, but also could be made of sort of commodity elements. So if you think about what is at a junkyard, right, you're going to have old cars, you're going to have old tires, we won't use the tires, but you're going to have copper wire, you're going to have things like aluminium alloys from window frames and so forth. So can we literally use junk and make high entropy alloys that are actually going to be corrosion resistant if all we need to achieve is passive films with unoxidized metal and so forth. And so we made this alloy, the aluminium iron manganese silicon alloy. As you can see, it turned out to be multi-phase, very, very hard, very low density compared to steel, but much better corrosion resistance than stainless steel. Quite remarkable, actually. So very, very corrosion resistant. This is sort of some new work that's been published. Again, we did this atomic emission spectroelectrochemistry, and we could see incongruent dissolution. You see a lot more silicon dissolution, surprisingly, even though silicon by itself is quite a stable material across a range of different pHs. You don't see terribly much dissolution of iron and manganese and so forth. So this is taking the dissolution signal and then passing out each of the contributions from each constituent element. And then when you do XPS, what you can see is this was angle-resolved XPS. You can see cationic fractions of more silicon in the film, then aluminium, then a bit of manganese, and effectively sort of no iron. Again, we saw a whole range of different unoxidized species. If you look at these sort of high-resolution spectra, you can see where you have the unoxidized state for each of these elements as well. So the same story repeats again and again and again. And this time, for sort of the reader's pleasure, rather than bore them with the point defect model overlays, we tried to draw a picture of how the passivity evolves in this particular alloy. So this particular alloy is like the one I showed earlier, the aluminium, titanium, chromium, vanadium. But actually what happens is after some early immersion, which you can only really understand by doing this atomic emission spectroelectrochemistry, you do get an enrichment of silicon. That silicon can also then redeposit and form a silicon hydroxide, which then becomes super, super, super stable. These sorts of, it creates compounds that are very much like the rocks that you find in nature. So really interesting that this alloy can be made. So there's a lot of interest in high entropy alloys, not just because of their mechanical properties now, but there's a lot of groups popping up that are looking at their corrosion. I can't do it justice, and I want to probably put a disclaimer out there now, but in the last 5 years, there's wonderful groups that are doing corrosion of high entropy alloys. There's a big group at Johns Hopkins, Northwestern in the US that are doing simulations as well. There's the University of Virginia. I know there's a group here in Colombia that's doing work on thin films as well. And so a lot of interesting work, and I'm sorry I can't do justice to all of it, but it's all super important and super fascinating. Now, everyone's looking at it from a different perspective. I've tried to talk about lightweight high entropy alloys that are corrosion resistant. Other people are looking at refractory high entropy alloys or coatings that are high entropy alloys. So there's different situations for everyone. So you probably wouldn't want to use this alloy at extremely high temperatures, but of course nickel, cobalt, chromium based or refractory type high entropy alloys could be suitable for things like aero engines, make them go hotter, faster. All right, so based on what we know now, I'm going to finish off with a little bit of a portal into some of the work I spoke about earlier this morning in a talk on artificial intelligence. But based on what we now know on high entropy alloys or multi-principal element alloys being useful, we do a lot of work in machine learning as well in the group. And what we've created is a compositionally complex alloy research directive interface GAN, so a generative adversarial network called Cardigan, which is for design and discovery of these particular alloys. What's interesting and why we needed to use GANs is these GANs use two neural networks. You use your classical machine learning and then another machine learning model, which you use random number generators to synthetically create data. And then you have a classifier to see whether that synthetically generated data is good and whether it matches your data set. And if it doesn't, junk that, you keep going, you keep going. So it's an adversarial technique where you sort of computationally penalize the synthetic producer of information. The reason why that was important is when we started doing this work, and this work was literally just published a couple of months ago, there was only 278 existing reports of high entropy alloys and other alloys like that. 3 ternaries, 28 quaternaries, 100 quinary, and 152 alloys that had 6 or more elements. Of these alloys, 101 was single-phase solid solutions, 79 had a mixed solid solution, and 98 had lots of secondary phases. So getting this particular data and realizing we can't design by using normal machine learning models actually took quite a lot of work because we had to scrape the literature quite a lot. This is what the model architecture looks like. That just shows you that you have your known data set from the literature that you feed through, but then you have a generator that uses random noise, and the classifier, as to whether the generator is performing well, uses the empirical models to see if it's matching what you would want from high entropy alloys. So I didn't want to do away with the no science, but what you see here is you see the neural network architecture that would predict the properties that you want, in our particular case, phase, for this particular cardigan, and what the inputs look like to get to that, and then what the inputs actually are. So these are the calculations that you do to try and get a high entropy alloy. Right, so it turns out what we did was we created 200,000 samples. 3,809 were selected as candidates for novel single-phase multi-principal element alloys. So using this model, we could have some fidelity that they were going to be single-phase. At least we thought. There's a bit of a plot twist at the end. And a down selection. Now, if you down select to try and get the complete optimum criteria where you would ideally get a face-centered cubic alloy and something with a low density and something with a relatively low price, we distilled it down to around about 188 alloys, and this is where you sort of plot them. You can see what the molar ratio of the composition looks like, so lots and lots and lots of data, and you can pick one of these alloys and you can make it. And these have never been made before. It's really, really interesting. Oh, I should probably say, just for fun, you know, one of the interesting things is, I know in the US and in Australia, you can't patent computationally designed alloys because for something to be patentable, it needs to be designed by a human, not a computer as a technicality. But if you make it and test it, then you can patent it. I just thought that might be a little bit of fun for you. So it was a single phase, I've copied the wrong one here. It turns out that it was a single phase FCC. I don't know why this is the wrong XRD plot for the particular alloy. You can see here that's got the data for that alloy, not that particular alloy. So that's my bad. But what was a real plot twist for us, so forget the XRD data for what's shown here, but if you do the XRD data of this alloy, I know I've been in Cancun too long, it turns out that you just get FCC peaks. And we thought, let's do the SEM and we'll just see a single phase FCC alloy. It turns out actually that nature is often quite funny and one step ahead. This particular alloy that we made has 2 phases, both of which are FCC, which the model was unable to predict. And that's very rare to see in high entropy alloys. Anyway, this is what the group looks like and how we do a lot of work. This is a hackathon. So rather than collecting data in the lab, a lot of the time we just sit around with a lot of food, like we'll block out a few hours of a day every 2 weeks, and we'll get a lot of food, you know, Red Bull, sweets, chips, things that keep people going, and then you scrape data for a long time, and then it shares the load. But I thought that would be an interesting way for you to see how we do some of our data collection as well computationally, because unless you see how it's done, you probably don't know, and you think that data might magically appear, but getting good data is the hardest thing. All right, so in summary, nearly done, 2 more slides. An obvious concluding remark is that these alloys are interesting and awesome. We haven't even scratched the surface yet globally from all the groups working on it. These alloys are amenable to additive manufacturing in net shape, so that's pretty cool. And their corrosion is very much underexplored and a recent endeavor. But it's a beautiful case study in terms of revisiting what we mean by passivity and actually understanding what passivity even is. Advanced characterization is, of course, very, very important in all that we do in materials research now, and there's been some great analysis in this conference so far. And of course, models of passivity need to evolve. But machine learning, I'll just finish on that, has a really big role to play in terms of objective design. So I'm just going to finish by going back to the beginning. If we're talking about future needs and future requirements, whether it's space, supersonic travel, a whole range of things, your next phone that might be implanted, it doesn't matter what it is. We now, have the tools and the opportunities to be a lot more objective. So if we remember that materials are anthropogenic, we're responsible for their properties, because we make them, even their bad properties, like corrosion, we have an important responsibility as well. So by using objective design, our mission is that by using machine learning, we'll be able to really start to close the sort of gap on the circularity loop and start to design materials that are specifically designed by using waste material in mind. So the one example I showed you today, the aluminium, iron, manganese, silicon alloy, is a really good example, right? We could conceivably continue to make that alloy many, many, many times over without needing to do mining, without needing to do ore processing, without, you can't do that for everything, but we have some responsibility to the planet to continue to think in that way. So I finished a little bit early, but thank you very much.
Okay, thank you very much your presentation, Professor Nick Birbilis. Any question?
Thank you. Thank you very much for the talk. Really interesting. Can you tell me again the thing that in the film you have the metal ions and the oxides, but it is a dynamic process. It's not steady, no? Like an oxide alone.
Yeah. Yeah, it's completely dynamic processes. So, if you could imagine yourself in the film, what you would see in these particular alloys, much more than you see in single component element alloys, is you would see a mixture of the different elements in non-stoichiometric components that's largely sort of self-balancing in terms of accommodating stresses, accommodating local reaction rates, accommodating a whole range of different things. So it's different for each of these high entropy alloys. Now, going into a lot of detail is something that I avoided doing here, but that's the sort of bread and butter of what I do. So it's a really, really good question. I don't have supporting slides to show you of what these partial reactions would be, but that's really the bread and butter of what we do. And you've reminded me to say something that I didn't say at all. So even though I've been talking about passivity like this sort of uniform thing, even the point defect model is still very archaic, even though some of the data we have now fits that model. Because if you think about things like grain boundaries, misorientations of crystals within an alloy and so forth, the model is far too primitive to even take that stuff into account as well. Yeah. There's some interesting work going on, obviously, with DFT and first principle calculations in the evolution of these films. Of course, the experimental correlation there, it becomes difficult because a lot of these calculations are done either at a few degrees Kelvin or in the presence of 1 or 2 molecules of water that don't really evolve in pH. So yeah, that's an exciting area as well. Yeah.
Question?
Thank you for a very nice talk. I'm not in the field in this area, but I have one question. Because you are using the AI and the machine learning, I was wondering that some of the materials you have, of course, skipped from the beginning in the periodic table.
Yeah.
In chemistry community, that we know, for example, the properties of materials are dependent on their surrounding and oxidation states. So if you, for example, nickel doesn't have to be magnetic.
Yeah.
Depends on the oxidation states. So do you think that you can also consider those things and adding some of the materials? You may find something very
It's a really, really good
unexpected
point.
results.
This is exactly why I love this conference, because it's not a corrosion or just a metals conference. You get these different insights. So you're 100% right. That model that I showed, the machine learning model, was the one I called Cardigan. Its output was really only to identify alloys that would be single phase. That model doesn't yet take into account corrosion information. So what the group was now doing, actually in that picture a couple of weeks ago, is they're trying to scrape corrosion information, both from our group, recent papers, and so forth. So yeah, that will really need to evolve to take into account these interactions. So you're 100% correct. We've barely scratched the surface, but I wanted to squeeze some of the machine learning in there today, because I wanted to use it as an opportunity to maybe make connections with others that are doing similar things and facing similar challenges. So yes, you're right.
Other question? Okay. The question again.
Hello. So I got the question about the K factors for different potential ranges. So could you please explain a bit more about this, why this happens?
Yeah. So what happens? So when you're getting incongruent dissolution, what's really interesting is that the total current that you get, so the alloy, you don't really think it's broken down universally, but there'll be some element which is well and truly above its oxidation potential. And so you'll see at different regimes, different sort of, before you see the ultimate breakdown of the alloy, you'll see different elements breaking down sort of in sequence beforehand, and then they will break down. It's really remarkable to see. That technique, I didn't invent it. I wish I did. It's just the most elegant technique, this atomic emission spectroelectrochemistry. So I would think probably in 5 or 10 years from now, most corrosion labs will probably have that arrangement, because there's optical emission spectrometers lying around in most chemistry departments that you just bring the two together. But yeah, that's a sort of a staggered breakdown.
Thanks.
And thanks everyone for coming this evening. It's been a real pleasure to be here.
The Mexican Material Society giving the recognition, Professor Birbilis, for your participation in the plenary conference. Thank you very much.
Thank you. Thank you, Facundo. Thank you very much. Thank you.